Hi everyone. Today we're going to be speaking about no-code PyTorch workload monitoring. My name is Shruti.
And I'm Yi-Ting.
And we're here from clockwork.io, where we were motivated to pursue this project because of a reality that I'm sure all of us in this room are all too familiar with. And that reality is that ML infrastructure fails. Not only that, but it fails often and it fails loudly. A recent study by Meta indicates that large-scale infrastructure issues have led to an overall 1.34x increase in average job completion time. What's worse, despite the fact that reliably running large-scale ML jobs is more important than ever nowadays, in the status quo, we not only have to deal with the consequences of these frequent failures, but also just with a great deal of confusion when it comes to understanding and detecting them. Let's consider the situation from two different perspectives. From the ML engineer's perspective, when a job that they're running starts to slow down or crashes, they have little to no visibility into the underlying root cause. They might spend a ton of time poring over their own code to see if they made some sort of problematic change. There are profilers that they can use, but these profilers often have such high overhead that they can't be used in real time, only in post-mortem debugging sessions. Not only that, but these profilers are often incredibly complicated and do deep dives into only a single node, such that even these debugging sessions might have no resolution. The ML engineer then has no choice but to just submit their job from an old checkpoint and perhaps ping the infra engineer. Now, from the infra engineer's perspective, they're stuck monitoring thousands of metrics across a variety of dashboards. Each dashboard says that it's going to offer insight into a different part of the cluster, the network, or the GPUs. Critically, these many metrics aren't put in context of the jobs that are actually running on the cluster at any given moment in time. This means that the infra engineer can't easily or effectively pinpoint why a particular job has slowed down. Not only that, but they can't adjudicate which of the many infra anomalies and alerts they're seeing on a daily basis is actually most tangibly impacting the health and usability of their cluster. It's here that we step in.
So now imagine this. An ML engineer suddenly notices a training job slowing down. And at the same time, the infra engineer immediately sees what infrastructure is failing, and that's affecting this specific job. This is what we want to bring. So we want to build on top of our sub-microsecond level, cross-stack, and cluster-wide observability to provide a single platform that pairs the infra issue with the training semantics, like a job or iteration step. This way, the ML and infra engineer can look at the problem through the same lens. No more guessing, no finger pointing, just shared visibility. So here's an example of what that looks like. At the top, we can see the iteration rate as the job runs. And in the middle section, we observe there was a slowdown. And going down the middle panel, we can see the infra flag raising PCIe congestion and also the correlated increase in data alert percentage time. So to achieve this level of visibility, we instrument multiple layers across the training stack. On the software side, we patch key PyTorch functions to get the training step breakdown. Here, as examples, we have the job iteration index and the percentage time span in forward and backward passes. And this is done through Python side package, so no code change is required. And going further, we have a Nickel plugin that tracks the queue pair level congestion by looking at the exact data path that the collective flow is taking. This gives us insights into where the in-bin traffic is getting stuck. Here we can see the one-way delay and good put at the queue pair level as examples. We also utilize eBPF to trace kernel scheduling and data transfer. So all of these help us collect rich job-level information. Now going deeper down the hardware stack, we use tools like ETHTool and open source DCGM to actively monitor the health of the device. Here we can see the CPU and GPU utilization, temperature, and so on. And last but not least, the network can make or break distributed training. So we build a probe mesh based on our clock synchronization technology to give us accurate one-way delay measurements and throughput for the standard in our DMA NICs. So putting all of these together, we're able to build a true end-to-end view of the cluster under load with no code change and very little overhead. And here, we have lots of metrics, but for the users, we want to provide the simplest interface. So we do attribution analysis to pinpoint a failure among hundreds of possible causes. We also quantify impact in terms of GPU hour to help prioritize what issue to resolve first. And all of the above metrics are compatible with Prometheus, so you can easily integrate it into the existing data pipeline. So now we'd like to show a quick demo of our workload monitoring.
For context, our demo is going to run across 4 hosts. These are called ECMP 4, 5, 6, and 7. Each of these hosts have 8 GPUs and 16 NICs, and we're going to be running 2 jobs across these 4 hosts, one slightly larger than the other just for a little bit of variation. The first, smaller job is going to run across ECMP 4 and 5. The larger job will run on ECMP 6 and 7. Now let's navigate to our dashboard. So the first graph that you can see here is called job iteration rate. What we'll see shortly is that we'll have 2 lines on this graph associated with the 2 jobs that I just mentioned. So that green line that has just started is the smaller job I mentioned running on ECMP 4 and 5. The yellow job is the larger job running on ECMP 6 and 7. You can see that the iteration rates look rather stable. That means your jobs are running as expected, they're running normally. But if you wanted even more granular insight into what is happening on your cluster while these jobs are running, you can scroll down to our iteration breakdown graphs. Here, we let you see what your GPUs are doing at any given moment in time. Specifically, we're plotting what % of a particular second is being spent on the forward pass, the backward pass, the data load, etc. This means that whether your job is running steady or not, you always know what work your GPU is doing and what exactly your cluster is looking like at any moment in time. Now, everything here looks rather steady because there are no current problems in our cluster, so let's create one. Here, Yi-Ting is initiating a script which will create congestion between ECMP 6 and ECMP 7. Recall that these are the 2 hosts involved in that yellow job over there. As we create congestion, these hosts will find it more difficult to communicate with each other, and because this is a distributed training job, we will see that the iteration rate has started to drop for that yellow host over there. Now, in the status quo, you'd have no insight into why your job has randomly started slowing down. In this case, though, you can see that we automatically flag there's an issue occurring in your system. More than just that, if you hover, you see that we've specifically attributed it to the NIC congestion problem. You can click View in Panel to learn even more. Once you go into this panel, you see again that job iteration rate that's dropped. You see that we have this flag, this graph here displaying that NIC congestion has now been detected. If you hover over that, you actually get even more insight into specifically what the offending NIC is, where is congestion occurring in your system. This means that the infra engineer knows now exactly what the problem in their cluster is and where to go to try and mitigate this issue. If they wanted even more information about the state of congestion in their system, they can scroll down to these variety of NIC metrics that we provide. You can see, for example, we're plotting one-way delays, which shows you that certain NICs have had their one-way delays shoot up. Not only that, but our throughput graph indicates that there's a new competing flow which didn't exist prior in the network. Once again, the infra engineer now knows exactly what to go do. They can kill this flow, and hopefully the job should start as normal. So let's do that. Here, Yi-Ting will exit out of the script so as to let up congestion in the network by killing that competing flow. As congestion in the network decreases, we will start to see that the iteration rate for this yellow job will start recovering, which we can already see happening, and we are no longer flagging the NIC congestion problem as one that's happening in our system. Okay, cool. So we've been able to solve a network problem. What if we created a different type of problem, a hardware one? Here, Yi-Ting is causing ECMP4's GPU 0 to become a straggler. Recall that ECMP4 is involved in that green job. And quickly we can see that as soon as we've messed with this GPU, the whole job associated with ECMP4 is starting to drop in terms of its iteration rate. Now, in the status quo, you'd have no insight into why this job is slowing down compared to why the one previously was slowing down. In our case, though, we once again immediately flag the problem as occurring in the system, and this time attribute it specifically to the GPU straggler problem. Once again, you can click View in Panel to learn more. Once you go into this panel, you'll see again that iteration rate, which has dropped. And alongside that, you'll see our anomaly graph, which indicates that the GPU straggler problem is occurring. And specifically, if you hover over that graph, you see we tell you exactly that it's ECMP4's GPU 0 that's acting like a straggler in your system. Once again, the infra engineer knows, okay, this is a particular problem in my cluster that I need to go address. Not only that, they don't even have to hypothesize about what's going wrong with the GPU. If you further hover here, you can click View in Panel, where we will tell you specifically that it's a clock slowdown that's been detected for this GPU. You can see that ECMP4's GPU 0's clock has become throttled. So now you know exactly what to do. We can reset the clock. Let's go ahead and do that. As Yi-Ting resets the clock, we'll see that the job iteration rate associated with the green job will start to recover. As we start to recover, we will also slowly notice that this is no longer a problem in our system. In this way, we'll eventually end up solving, in the matter of a couple minutes, 2 infrastructure issues, whereas in the status quo, we may not even have been able to detect and properly understand them. In this way, Clockwork is able to bridge the comprehension gap between the workloads that are running and the infrastructure upon which they run. Thank you. I don't know if we have time for questions, do we? Okay, cool. Yes, question?
Hi. Sorry, I think I missed maybe the first couple of minutes, but I think, I don't know if you already covered it, but the question is, how do you inject do you inject essentially instructions in the CUDA code to get information about the NIC, for example, or the GPU? Because I feel like that's way more low level than you can generally get information about. So how do you get that?
So like we have different layers. So like at the very top layer is the PyTorch layer, and what we use is I guess we can go back to this slide. So these are the layers that we inject. So like at the PyTorch, it's like no code, it's like a side package, and then we also use eBPF to trace certain like CUDA kernel scheduling, and also we have our own like measurements for like networks and GPU by using our like ProMesh or like DCGem. So we're basically combining all of these cross-stack measurements to be able to construct the relation between the infra and the job. So we're at time. We're happy to take any more questions out the corridor. Thank you.